Welcome back. This is the Tutor Wizard. I'm Adrian. Please subscribe right here. Hit the notification bell for notifications for this series and a bunch of others on our channel. We're doing multivariable calculus. This is chapter 3, vector calculus, and we're doing 3.6, which is parametric surfaces. It is going to be the analog to parameterizing curves in the plane. Now we're going to parameterize surfaces in 3 space. This lecture specifically, we're going to give the definition of the parameterization of a surface S and a couple examples. Let's do it. We're going to try to mimic, as we always do, extending the idea of now a surface integral, just like we had line integrals over curves. So first, what do we need? We needed a curve and how to parameterize those things. And then we saw if it's a rectangle and it's orientated, that's a horrible business. And then we use Green's theorem, that's better. Now what we're going to do is we're going to have to parameterize a surface in 3 space. And guess what? We're going to mimic. So if we have a space curve, I don't really like that terminology. I would rephrase it as we have a curve in 3-dimensional space, or a space curve. This is space physics, space math. This is rocket science. We have a space curve and we use the position vector r of t, which is viewing the coordinates as functions of a parameter t, and then the parameter ranges from a to b. We're going to use the exact same idea to parameterize a surface. We can parameterize a surface using a vector function of 2 variables u and v now, and each coordinate depends on both of those coordinates, where u and v range over a domain. Pictorially, we have a domain in the uv plane. What we're going to then do is map this, and the best way to view this is what the vector function is doing is, as you range over every point over D, this vector in 3-dimensional space, as you move the points over this, that vector will trace out the surface, is what's happening pictorially. But analytically, we're going to describe the surface now as a function of 2 parameters, u and v. Let's do a couple examples of that. Our first example is just getting used to this. This is what you should be doing also, but I'll practice it and guide the way. They just gave me this way of saying, now I finally have a surface and you're used to viewing it in Cartesian, and now we're going to go back and forth. This one, I've flipped it, and usually we give you a Cartesian one and say, put it into the parameterization in u and v or something like this, or rho and theta and phi, something like this. What I've done already is done that and want you to reverse engineer and try to tell me in regular Cartesian coordinates what this surface is. I have a surface parameterized by 2 variables u and v, where the first coordinate x is v, y is cos u, and z is sine u. First of all, what is this? This is going to give me, which is 1. What that tells me is in the yz plane, we're on a circle of radius 1. And then what we can see is x is allowed to be anything it wants. So if x is the axis, is now going to come out of the board. It can get there, so it's going to be a circular cylinder with its axis, the x-axis, in 3 space. What is that going to look like? Draw the object first. I want it to go along the x-axis, so there's the x-axis. Now what I do is, there's my origin, there's z, there's y, and then it's the circle in the x or the yz plane, and then x is allowed to be any value. So what is this? This is the circular cylinder with axis along the x-axis in 3 space with radius 1. You should practice viewing, and so that you could picture what the parameterization is telling you. This is the weird way of saying what you were used to seeing is y squared plus z squared equals 1. Therefore, let's try the reverse of that. Now let's give ourselves this familiar sphere and parameterize that somehow. Or in example 2, we're going to go the other way. What I'm going to do is give you the familiar sphere in Cartesian, x squared plus y squared plus z squared equals a squared. And I want a parameterization of this. Guess what I'm going to use? I'm going to use spherical coordinates. What that says, remember, a is a fixed number, the radius. Then what I'm going to say is, well, I have a sphere of radius a. What I want is a parameterization of that. And so if I could think about, say, an angle from 0 to pi, and then I could think about another angle, say theta, from 0 to 2 pi, I could probably use spherical coordinates to parameterize this sphere. And it's only going to be 2 variables now because a is a fixed number. Phi and theta change. A doesn't change anymore. What that tells me now is x squared plus y squared plus z squared equals a squared is going to become what as a parameterization? I'm going to say x is a sine phi cos theta, y is a sine phi sine theta, and z is equal to a cos phi. And so that parameterization as a vector now, this is why I did this one, because it's nice and easy, because you're not too horribly surprised by this because you've already seen spherical coordinates. If you've been watching my videos in the list, you definitely have. Then what is this phrasing it as our vector function of two parameters? My parameters are 0 is less than or equal to phi is less than or equal to pi, and 0 is less than or equal to theta is less than or equal to 2 pi. And our vector function of the two variables theta and phi is equal to a sine phi cos theta, a sine phi sine theta, and a cos phi. This is the parameterization of that surface now. Ranging over this and viewing that vector now that we would have from there, it's going to trace out all the points on the sphere all the way around as you go like this, and then from here to here it will trace out every single point on that sphere. Please subscribe right here, hit the notification bell, get notifications for this series and a bunch of other ones on our channel. Next time, what are we going to do? You'll have to find out.